Kc. Okay, I think yesterday I would have actually done like up to here. Okay, when you have this equation, and let's say it's gas, gas, and gas. Okay, so we can actually write down what we call as a Kc. Okay, Kc is called equilibrium constant. So the equilibrium constant is actually written from the product. So the product, the concentration is NH3 to the power of 2. I put 2 over there. Divided by concentration of nitrogen to the power of 1. Okay, 1. And then times the concentration of hydrogen to the power of 3. Okay. And if I have another equation, let's say, for example, 2HI to give you H2 plus I2, let's say they are gas also. You can actually represent using Kc. Kc equals to concentration of H2 to the power of 1 times concentration of I2 to the power of 1 divided by concentration of Hi to the power of 2. Okay, so please actually remember one thing: the units are going to be different at all situations. Okay, so units, okay, if you want to calculate the unit, concentration is mole per dm cube. So if you have this to the power of 2, so mole dm to the power of 2 divided by mole per dm to the power of 1 and 3 is 4. So use your maths, get 2 and then this is 2. So you will get mole, okay, if this one bring it up is -2, dm -6, bring it up to the power of 6. So this is going to be the units. Okay, if I want to actually calculate the unit for this, okay, this one is going to be mole per dm cube, 1 and 1, so 2 mole per dm cube to the power of 2, cancel, cancel. Okay, so this one has no unit. Okay, so you can see that, okay, the Kc, Kc is equilibrium constant, and they can also have different units. Okay, it can be also no units. And I want you to also remember when it comes to Kc, okay, we can actually calculate for liquid, we can calculate for aqueous, we can calculate for gas, but we do not include solid in our calculation for Kc. Okay, we do not include solid in our calculation for Kc. The reason, if they ask you the reason, solid, the concentration is always constant. Okay, so we do not involve any concentration that is constant in our Kc calculation. Okay, that is going to be the reason. Then I want you to also remember, okay, when it comes to position of the equilibrium, okay, we have learned about the position of the equilibrium. The position of the equilibrium can move to the right, can move to the left, okay, according to LCP, okay, Le Chatelier's principle, okay, if you actually use the term to pronounce, yeah, okay, but it's actually like this. Okay, so if you use this principle, okay, if you use this principle, what are the things that will affect the position of the equilibrium? You have number one, concentration will affect the position of the equilibrium. Change in pressure will affect the position of the equilibrium. Okay, we have went through this yesterday. And number three, change in temperature will affect the position of the equilibrium. But how about catalyst? Nathan, do you think catalyst affects position of the equilibrium?
No.
No. So they do not affect the position of the equilibrium, but catalyst affects the rate of the reaction, and to be exact, both, okay, forward and reverse reaction. So your equilibrium can be achieved faster. But do not forget, okay, do not forget, we have also learned rate of reaction. Now, rate of reaction will generally, if you look at the rate of reaction, your rate of reaction when the concentration is high, pressure is high, temperature is high, generally the rate of reaction is going to be higher. How does it imply when it comes to reversible equation? Now, we know the position of the equilibrium will shift according to all this, okay? But when it comes to rate of reaction, high concentration, high pressure, and high temperature, they will make the speed of the reaction to be faster. Okay, to be exact, the speed of both forward and reverse will be faster. So it means what's going to happen? You are going to have the equilibrium to be achieved at faster rate, not only when catalyst is there. You are going to achieve the equilibrium at faster rate when you have these conditions as well. Okay, achieving it fast and achieving more yield is different. What is yield? Production. Okay, so the production might be less. Okay, like for example, if you want to actually produce ammonia, for example, this is the yield, the product yield. Okay, it's supposed to be, if you want to produce more ammonia, it means the position of the equilibrium must be shifted to the right. Okay, but sometimes the position of the equilibrium can be shifted to the left. But okay, that will actually cause your production yield or the yield of your ammonia to become less. But that particular less yield can be formed at higher rate. It means it can be formed faster. Okay, so later I'll show you some examples of questions so that you can understand what I'm talking about over here. Okay, now the next part, okay, that I want to teach is the KP. Now KP is similar, okay, to your KC, but KP is specific for gases. Okay, like you see the KC you can use for gas, you can use for liquid, you can use for aqueous. But KP is only for gas, so therefore I'm going to actually use this example. If I use this example, if I want to represent using KP, it's almost the same. KP equals to, we are going to use this term called partial pressure. Okay, partial pressure. What is partial pressure? I'll tell you in a while. Okay, KP equals to partial pressure of ammonia, bracket again to the power of 2, divided by partial pressure of nitrogen times partial pressure of hydrogen to the power of 3. And this partial pressure can be in kilopascal, can be in pascal, can be in atmospheric pressure, we call it ATM. So unit, when it comes to unit, it's the same thing for KC. Okay, let's say if I'm using Pascal, Pascal to the power of 2 divided by Pascal to the power of 4. Okay, you cancel and cancel. Pascal to 1 divided by Pascal to the power of 2. So this is going to be the unit. Okay, same way for KC. Okay, but maybe some of you actually will get confused about what is partial pressure. Okay, what is partial pressure? So I'll explain to you what is partial pressure. If let's say this is going to be a particular container, a closed container, whatever particles that you have, okay, inside, they will contribute to the pressure. Okay, they will contribute to the pressure. Imagine you have 3 particles over there, and all these 3 particles will contribute to the pressure towards the wall of the container, okay, of this container. Okay, they are going to hit the container and then they will contribute towards that pressure. Imagine the pressure exerted towards the container is going to be a total pressure. Let's say I say total pressure, okay, PT. That's going to be a total pressure. Now, there is no other particles inside the container other than, let's say I name this. This is A, this is B, this is C. So all the pressure is only contributed by A, B, and C. So it means that I can just say pressure total is contributed by pressure of A plus pressure of B plus pressure of C. And this is what we call as partial pressure. Okay, partial pressure. Why partial pressure? Okay, let's say your total pressure is going to be 10. This might be 2, this might be 2, and this might be 6, equals to 10. So from where I get this number? Okay, why suddenly PA is 2? Why PB is 2? Why PC is suddenly 6? Probably there's another 2 more C there. It means the number of moles of C is more compared to the number of moles of A and B. Of course, if you have something that is more, they will have a bigger pressure. So if you look at it, now you can actually see they will work according to the fraction. How do we calculate those fraction? Okay, this calculation is quite simple. Okay, like for example, if let's say I have A plus B to give you 2C, for example, and all of them are gas. And I told you about ice. Okay, initial change and equilibrium. Forget about I and C now. Let's say I give you a value at equilibrium. We are talking about 1 dm cube. The entire container is in 1 dm cube. Okay, let's say we are talking about number of moles, and you found out at equilibrium there's 2 moles of this, 2 moles of this, and there is, okay, just ignore the proportion, there's 3 moles of this, okay, at equilibrium. Now, if I want to write the Kp, I will write Kp equals to partial pressure of C to the power of 2 divided by partial pressure of A times partial pressure of B. How do I calculate all this partial pressure? Very simple. Okay, you calculate like this. In this particular container, I have 2 moles of A. I have 2 moles of B. And I have 3 moles of C. Okay. Now, we need to break them down into fractions. How do you break them down into fractions? So let's say for A, what is your partial pressure of A? Your partial pressure of A is 2 moles out of how many total moles? 2 plus 2 plus 3. That's going to be 7. 2 out of 7. And that is going to be times with your overall pressure. Let's say I'm going to use PT. Thompson, can you follow until here?
I'm so confused a bit.
Okay. The total pressure will be given to you. Okay, the total pressure will be given to you. Just follow, yeah. So let's say, for example, PB. If you look at PB, there's 2. How do I put 2 over 7 times PT? How do I calculate for C then? 3 over 7 times PT. What does it mean? It means that when I add all these together, PA plus PB plus PC, I supposed to get PT total. You just try to add 2 over 7 plus 2 over 7 plus 3 over 7. You will get 7 over 7, which is going to be 1 PT. So it means that is going to be what we call as partial pressure. So partial pressure, you have that already. So what you need to do, you just need to calculate the partial pressure, put in the values. PA, you put it there. PB, you put it there. PC, you put it there. And then you calculate like normal. Okay. So Mr. Gopi, I cannot understand at all. Okay. In that case, let's try questions. Okay. So I will show you the questions. Let's try from the beginning. Okay, good enough. So here, let us try related to KP first, yeah. Okay, let's try question number 7 first. So here you have methanol can be produced and all of them are gas. And I want to actually write what is Kp. So Kp equals to partial pressure of CH3OH divided by partial pressure of H2 to the power of 2 times partial pressure of CO. So you go and actually find which one is going to be the correct answer, okay? And you will see that this is going to be the correct answer. Quite simple, straightforward, okay? So let's actually keep on going to more difficult one. Hold on, yeah, let me select. Okay, let's see this. So you have, okay, all of them in gaseous form. And they're asking you about the units. And you can see all of them in kPa. So it means we are using kPa. So I will write down Kp equals to, not concentration. Okay, this one is partial pressure. Partial pressure of CH4 times partial pressure of H2O, partial pressure of CO times partial pressure of H2, don't forget, to the power of 3. And then they are asking for the unit. So if the unit here is kilopascal, kilopascal to the power of 2 divided by kilopascal to the power of 4. So you cancel, this is 2, so kPa negative 2 if you bring it up. Okay, so the answer is going to be D. Quite simple, right? Still level 1. Okay, still level 1. Let's try this question. Okay, now this one is actually a lot of things. Yeah, if you see, there's so many things that is happening. So you see, they say that HCl are mixed. Okay, HCl is mixed in a sealed container with oxygen, so plus oxygen, and they say that it gives you Cl2 plus H2O. Okay, and then I do not know whether it's equilibrium or not, but I think the moment I see this question, equilibrium mixture, so I know for sure I need to change the arrow to become like this. And then the next thing that I need to do is to balance the equation. So how do I balance the equation? 2Cl, I put 2 there. And then oxygen, okay, there's only 1 here. So I put half. It's all balanced now. Okay, but if you want to times everything by 2, so go ahead, 4HCl plus O2, 2Cl2 plus 2H2O. That's going to be the equation. Okay, that's the equation. So what is the first thing that we need to do? You need to actually do this ICE, initial, change, and equilibrium. Now, they say that when 1.6 mole are mixed, so that was initial, 1.6 initial, and they are mixed with 0.5 of this. That's also initial. And initially, there's nothing, no product. Okay, no product. And then they say 0.6 mole of Cl2 are formed. So that is actually your equilibrium. At 0.6, they are formed, and this is 0.6, they are formed. So these are the information that that is given to me. Okay, I need to actually figure out the other information myself. So how do I figure out? From 0, how come magically become 0.6? Of course, plus 0.6. Of course, plus 0.6. So here, do remember, okay, I want to erase the first equation. Do remember, every 4 moles react with 1 mole to give you 2 moles and 2 moles. It means that we will look at the change. It means that this ratio 2 is representing 0.6. This ratio 2 represents 0.6. If 1, what should be appearing here? Megan? 2, 0.6. 1?
0.3.
Yeah. If 4, if 1 is 0.3, 4 is, right?
Um,
1.
1.2.
Yeah, 1.2. Now, what you need to add over here is, okay, you need to actually think about, okay, this is plus 0.6 plus 0.6 because they are product. These are reactants. It must be minus and minus. Okay, it must be minus and minus. So what you need to do next is to find out what is at equilibrium. 1.6 minus 1.2, you will get 0.4. 0.5 minus 0.3, you will get 0.2. Those are the number of moles at equilibrium. So that is actually what they ask you to calculate. Calculate the amount of moles in the equilibrium mixture, and I have calculated the number of moles of HCl, which is 0.4. How about O2? 0.2. Done, yeah? So you have to use the ice, okay? Initial, change, and equilibrium. Next. Calculate the mole fraction of Cl2. The moment you see mole fraction, do remember these are the heroes of the story. We don't bother about others. Sir, how did it go from 1.2 to 0.4? 1.6 minus 1.2. Initial minus the change. Owen, Ken? Okay. So it's all the same thing. How can you get 0.2, 0.5 minus 0.3? So initial. How can we get 0.6? 0 plus 0.6. Okay. Now, so here, okay, calculate the mole fraction. These are the hero of the story. We are not bothered about I and C anymore. Okay. So the total, first find out the total number of moles. Total number of moles is going to be 0.4 plus 0.2 plus 0.6 plus 0.6. That's 1.2, 1.4, 1.8. That's 1.8. So if I want to find the mole fraction of Cl2, simple. What is my mole fraction? Okay, not partial fraction, but they say mole fraction. Mole fraction is 0.6 divided by total number of moles, 1.8. That is your mole fraction, which is 6 divided by 18. That's going to be 1/3. That's your mole fraction. Hence, the partial pressure of Cl2. Partial pressure is 1/3, the mole fraction, you times with the total pressure. So what is the total pressure? They have given you the total pressure. So 1.5 times 10 to the power of 5. Okay. And you will get, okay, this one is going to be 0.5 times 10, 5. So this one is 5 times 10 to the power of 4. You'll get that. So it means this is just the pressure exerted by Cl2. You still have the pressure of this. You still have the pressure of this. You still have the pressure of this. But I just want to ask you one question. Okay, later I will actually show you a question related to this. Now, we know that Cl2 is a different molecule compared to water. Okay. And we know that, okay, they follow the same changes as 0.6 and 0.6 over here. Why? Because the same ratio. It means the 2 and 2. Okay. And if I actually calculate the mole fraction of H2O, I just want you to see the mole fraction of H2O. The mole fraction of H2O is 0.6 divided by 1.8, which is also 1.3, 1/3. And if I ask you, what is the partial pressure of H2O? Okay, partial pressure of H2O is also 1/3 times the total pressure, which is 1.5 times 10 to the power of 5. And you will get 5 times 10 to the power of 4. What does it tell you over here? Your partial pressure of Cl2 and H2O, they are the same given if they have the same number of moles here. I hope you understand this part. Okay. Later, I will actually revisit again. Yeah. So let's revisit later. Okay. Now, coming back to the questions. Okay. So this one, they didn't ask us to solve this, but let's actually try to solve. Okay. The question proceeded, and then they say that, okay, they give you the formula. Not all the time they give you the formula. Okay. But they gave you the formula. And then they say this is at equilibrium, and they have already have the partial pressure for you. You don't need to calculate. So they say use this the expression, okay, and calculate the value of Kp. Very easy. Kp, just put in the data. 3.6 times 10 to the power of 4 to the power of 2 times partial pressure of H2O. 3.6 times 10 to the power of 4, 2. If you are wondering why shouldn't we times with total pressure and so on, no need. This is already partial pressure. You don't need to do that. Okay. And divided by, someone help me to calculate. I think if I calculate, it will take a longer time. Okay, just start to calculate. 023.0 times 10 to the power of 4. Okay, and then state the unit. Okay, state the unit. So this one is going to be Pascal to the power of 4, Pascal to the power of 5. So cancel, cancel. You will get Pascal to the power of -1. So what is Kp? Someone help me to calculate.
1.05 times 10 to the power of -5.
Okay, just check, yeah. So 1.05 times 10 to the power of -5. Okay, I just follow your answer only. All right. Now, so here, the next question is the reaction is repeated without catalyst. So here they actually put catalyst. Okay, they put catalyst. And then they repeated without the catalyst. State the effect of this on Kp. Okay, Catherine, what is going to be the effect of without the catalyst on Kp?
The reaction slow down.
No.
No effect.
Kp, no change. Why? Kp and Kc only affected by temperature. Okay, remember this. Kp and Kc, they are only affected by temperature. So if you use catalyst and so on, there will not be any effect towards Kp. Okay, let's go to here again from the beginning. Okay, I think good enough. So let's actually start from the beginning. You see, this is write what is going to be Kc. So if you write the Kc, okay, Kc, let me change the ink. Okay, so Kc is going to be NH3 to the power of 2, concentration of nitrogen, concentration of H2 to the power of 3. Okay, so this might be correct, this might be correct. Okay, just be very careful. Okay, okay, it's not showing on the screen. Let's wait for a while. Let me share the screen again. Okay. So it's a bit slow, but it's okay. You can see here, this is plus V1 times, okay? So the answer will be D. Okay, that's going to be the answer for this, okay? Now, so if you have this number 2 here, they say that sulfur dioxide and oxygen react in gas phase. Which one is going to be correct? Increasing pressure. Okay, so now talking about pressure, what you need to do? 2 and 1, 3, do that first. Increase pressure. Pressure is increased according to LCP. I need to bring down the pressure. How do I bring down the pressure? By going towards the side that has less molecules. So it will go to the right. When it goes to the right, you can see SO3 will be formed more, okay, because position is going there. So this is correct. Increasing the temperature. Let's talk about temperature then. Okay. Temperature lowers the value of equilibrium constant. Okay, now we know that equilibrium constant is affected by temperature only, but we don't know whether it's going to go up or go down. So what you need to do? So you follow what I taught you. Put a hand over there. This is going to be negative. So this is hot. This is going to be cold. So when you increase the temperature, I need to decrease the temperature. How do you decrease the temperature? By shifting the position from hot to cold. When you shift that position, what happens is you are using up SO3 to produce more SO2 and O2. So when I write down the Kp is supposed to be SO3 partial pressure to the power of 2 divided by partial pressure of SO2 to the power of 2 times partial pressure of O2. When I do that, I know that SO2 is increasing, O2 is increasing, SO3 decreasing because it's moving to the left. You see something smaller divided by something that is bigger. You are going to get a smaller value or bigger value, Elizabeth Donna?
Smaller.
Yeah, so smaller value. It lowers the equilibrium constant. That is correct. Okay, that is correct. The presence of vanadium pentaoxide catalyst, correct catalyst, okay, they increase the equilibrium yield of SO3. For even, do you think that is true?
No.
Okay, catalyst only increases the rate of forward and backward, but they do not change the position, or they do not actually increase any kind of yield. Okay, so this is wrong. The answer is 1 and 2. Okay, let's move on. Okay, here, ammonia is produced in Haber process. Okay, a fault in temperature control resulted in the temperature changing to 600 degrees Celsius for 2 hours. What effect? Also, you will be asking, 600, what is going to be the initial temperature? Did they forget to write down the initial temperature? They didn't forget. Okay, you need to actually know that the moment you see this symbol over there, that means at standard temperature and pressure, 25 degrees Celsius. So the fault that happened made the temperature to become 600 degrees Celsius. So the change in equilibrium that is going to happen is your temperature is going to be increased. Okay, that is the change in equilibrium. So what they need to do, okay, let's actually do the same thing. Put the hand. This is hot. This is cold. When you increase the temperature, according to LCP, you bring the temperature down. How do you bring the temperature down? By hot changing into cold. So the position is moving to the left. When it is moving to the left, we are talking about equilibrium yield of the ammonia, yeah, because they say ammonia. Ammonia will become less. Okay. So yield must be decreased, cannot be increased. Then is it going to be faster or slower? Okay, is it faster or slower? Then look at this. Temperature is high. I told you the rate of reaction. Pressure higher, temperature higher. You put catalyst, you put concentration that is higher. All these will increase the rate. Okay, all these will increase the rate. So the rate is definitely going to be faster. I think I mentioned about this just now. Okay, if you can recall, I told you the rate can be fast, but the equilibrium can be less. Okay, this is one of the things that I mentioned earlier. Number 4, easy question. Okay, here they say that for reaction shown, equilibrium is established. Is this important? Not important. Okay, the equilibrium constant Kp, let's actually write down Kp is partial pressure of NO2 to the power of 2 divided by partial pressure of N2O4. So this value they have given 9.8. The partial pressure at equilibrium is 80. So this one is 80. You just need to find this. Quite easy. Partial pressure of NO2 equals to 80 times 9.8 square root. Quickly calculate, tell me the answer, then we'll move on. The unit also quite simple, yeah. kPa to the power of 2 divided by kPa. Cancel, cancel, kilopascal. Josh, what's the answer?
28.
Yep. Okay, let's move on. Remember, there is one question I told you we will revisit. Now, you see hydrogen and carbon dioxide, they'll give you water and CO. 1 mole and 1 mole. Okay, you see here what is going to be something that you need to know. At equilibrium, the partial pressure of H2 and CO2, they are given. Kp is given. They want you only CO. The question is, how about H2O? Okay, if you still haven't reached to that, I will still write down the equation. Kp is partial pressure of CO times partial pressure of H2O. Divided by partial pressure of H2 times partial pressure of CO2. And they have given you the data. This is going to be Kp is going to be 10. Kp is 0.288. Partial pressure of H2 is given. Partial pressure of CO2 is given. So I'll write down H2 is 10. CO2 is going to be 10. I want to find out partial pressure of CO. But how about partial pressure of water? Ryan, how to do this? Let's revisit. Two and two. Okay, 2 and 2. And we calculated the partial pressure of Cl2. Okay, was this. And when I see for water is a different thing. Okay, but when I calculate the partial pressure, because of the 2 and 2, okay, the mole fraction will be the same. And the partial pressure is the same. That's the reason why I told you we will revisit this later. Why? If you are not given that data, you need to, you know that it's supposed to be the same. You know that this PH2O is the same as PCO. This value and this value, they are the same. Okay, so I can just simply say this is same, PCO. Basically, P partial pressure of CO is the same as partial pressure of H2O. Why? Because 1 and 1. Be very certain on this. Okay. If you are not sure, please refer to the part that I said I will revisit later. I can share this document to you, the work document to you later. Yeah. So here, okay, when I have this, what I need to do is just to calculate. So this is 100. When you times that, you will get 28.8 equals to partial pressure of this. Then you need to square root. You'll get 8. So the part over here is this one. It's not that we ignore, okay? It's the same as that. And this applies only this one, and this one is the same value. It can be also be applied if it is 2 and 2 or 3 and 3. Okay. Number 6. Question looks so difficult, but it's very easy. They have done this investigation initially here, and they have the KP value is Y. Then they do another investigation, the value of KP to become Z. So they ask you to compare Y and Z. And when you compare, pressure increase, but temperature remains the same. So how do you compare? Owen?
Sorry, sir. What was the question, sir?
The question is what is the relationship between Y and Z?
Not sure, sir.
Kp and Kc is only affected by temperature. What can you say about the temperature? The temperature is the same. If the temperature is the same, pressure change doesn't matter to Kp and Kc. So it means that this Y must be the same as Z. The same concept. Can understand now, Owen? Okay. Even okay?
Yeah.
Okay, let's move on here. It looks difficult, but it's actually very easy. Yeah? You just need to check. Yeah. So number 8. Which statements are correct for reversible reaction at equilibrium? All species at equal concentration. Audrey, do you think that's correct?
No.
Equal, definitely no. Okay. All concentration remains constant. Yes. The rate of forward equals to rate of reverse. Yes. The answer is 2 and 3. Okay, let's actually do some questions that involves a little bit more thinking. Yeah. So here, okay, you have the condition to favor formation of hydrogen. To favor formation of hydrogen means, Frederick, is it supposed to be shifted to the left or shifted to the right?
To the right.
To the right. So you need to figure out ways to make it shift to the right. Okay. Now let's actually look at the pressure. Okay. Pressure, the moment you see pressure, what we do? 1 and 1, you add 2. 1 and 3, you add 4. Shifted to the right, you need to actually work backwards over here. 2 to become 4. It means why I have to change 2 to become 4? It means what I'm trying to do. I am trying to increase the pressure if it is shifted to the right. Why? Because less number of moles to make more number of particles. Yeah, pressure is increased. Why we do that? Okay, because LCP. This is actually because of LCP. Okay, Can you still hear me? Josh, can you still hear me? Okay, let me actually try to connect, share the screen again. Okay, let me repeat again. 2 to 4, it means what I am doing, I'm trying to increase the pressure. I have to work backwards, yeah. So I'm increasing the pressure. Why I'm increasing the pressure according to LCP? Because they have reduced the pressure. They reduce pressure. I need to increase pressure. I move to the right. So this is going to be your answer, low pressure. So the answer can be either C or D. So let's actually move on. Okay, let's say about temperature now. So I erase this this part again. Now you want it to go to the right. So what you do, you just put the hand. This is going to be cold. This is hot. What is happening? Hot to become cold. So what I'm trying to do, I am trying to bring the temperature down because of LCP. Why I'm bringing that down? Because the temperature was up. So this is what I want. You are just working backwards. Okay. Is it okay, Nathan? Okay, let's move on. This one very easy. I think I put combination of easy and difficult questions. So this one is just need to calculate only Kc. Yeah? Kc equals to concentration of this to the power of 2 divided by concentration of N2, concentration of H2 to the power of 3. Just put in the values. 0.6 to the power of 2, 0.2 times H2 is 0.3. Don't forget to the power of 3. Help me to calculate. Giuliano, tell me the answer.
66.7.
Okay. Here, let's try a question. This one also involves some thinking, yeah. So in a particular reversible reaction, the yield of the product is increased. Okay, the product is increased means the position is shifted to the right. So they say that it increase if the temperatures increase. Okay, let's actually see here. Let's say a particular reaction, A plus B to give you C. Temperature is increased. You have positive and negative. Let's say I just want to try with a negative, for example. I put the hand. Hot, cold. When temperature is increased, I need to bring down the temperature. How do I bring down the temperature? By moving to the left. Okay. So it means I want it to go to the right. So of course, negative cannot be the answer. Okay. Cancel it. Cannot. So the next part is pressure. Okay, let's actually talk about pressure. So A plus B to give you C. 2 to 1. Okay, number of moles. And let's say I try to decrease the pressure. Pressure decrease. What I need to do, I need to increase the pressure. How do I increase the pressure? By moving towards more. It's going to the left. It means I should not have a bigger number here. Okay, so let's see. This is a bigger number, smaller number. I should not have that. This is 2. This is 4. Okay, so when I decrease the pressure, let's see here. When I decrease the pressure, I need to increase the pressure. I will go to the right. So it satisfies this. The answer is A. This is also requires you to analyze, cancel, think. Next, similar. Which condition of pressure and temperature favors the reverse reaction? So I want it to go to the left. So let's actually figure out how to make it to go to the left. So this is going to be negative, so hot. This is cold. How do I make it to change from hot to cold? What I'm doing, you can actually do it the reverse way. Yeah? Hot to cold. What I'm doing, I'm actually bringing down the temperature. Why I am bringing it down? Because the temperature was high just now. Okay. And then let's actually look at the number of moles. Okay. Number of moles. This is 3. This is 2. And I want it to go this side. What am I doing? I am trying to increase the pressure because I'm moving it from less to become more. Why I am doing that? Because earlier it was down. So the answer is low. I hope you understand whatever things that I'm doing over here. Okay. I think still have time. 1 more minute. Okay. Which statement about effect of catalyst on a reversible reaction is correct? The activation energy stays the same. Thompson, do you think so?
No, sir.
No, activation energy will go down. All the catalyst provides an alternative pathway with lower activation energy. Yeah, so whatever way that you actually memorized last time. Okay, the composition of mixture stays the same. Now this might be a bit confusing, I think, related to the term that is used. Same doesn't mean equal in this case. Okay, but let's actually come back to that later. Rate of backward reaction stays the same. No, rate of both is going to increase. The value of equilibrium constant changes. No, the value of equilibrium constant is only going to change with temperature. So the composition of mixture stays the same. Imagine at equilibrium, that's going to be 432. Okay, at ice. Yeah, so you have E, 432. So if you add catalyst, the equilibrium is still going to be 432. That is what they mean by same. It's not equal. This is telling us it's going to be constant. Okay, so the answer is B. Okay, I think that's it. Okay, there's a lot of questions for you to try. Okay, but I will actually really go through all these questions with you. Okay, but you can actually make it easier by trying to go through those questions by yourself as well. Okay, any questions before I end?